Good morning. We will start SolidWorks simulation. So today I'm going to look at three topics. The first one is analysis of contact stresses. So here what we are going to do is this is also kind of a static analysis. We have two plates like this. So when these two plates touches with each other, uh, there will be a stress forming here. So this side is fixed and I'm going to apply 1000 newtons vertically down like this. So we'll see what are the stresses developing in this area. So we will apply some loads, fix this side, and we will discuss about the contacts. Last week also I discussed about the contact methods. Then after we do the simulation, we will get some results like this. So we can see what are the stresses forming in this common area, contact area. So that's the exercise here. So we will start it. So I have opened my file. If you look at your folders given, I have given a file called plates and two plates. So the two plate file is the SolidWorks assembly. Two plates will be using this single plate. It's a the single plate has been used in both cases. So if you look at the SolidWorks design, you have the plate here and you have the same plate here. Actually, we didn't cover this assembly area with you, but it's not a difficult area. So they have assembled these two plates and they have got this kind of a common interface. So you can open this two plates assembly file. So once you open the assembly file, you will get this kind of a model. So I'm going to apply these loads given. So we are going to do a static analysis. New study. Same static analysis. In your syllabus, they ask us to do static only. So that's why I'm doing static. We have thermal frequency buckling. So today I'm going to look at buckling also a little bit. And the other areas we will not going to do because it's not asked by this module outline. So we are going to do static here again. Okay. Now, since this is an assembly design under component contacts, they have mentioned this as a global contact. So last time also I discussed this. Uh, what is the meaning of this one is this contact is treated as a say very perfect bond. So if you want to override these things, you can right click and define a contact set. So if you want, you can override this condition, global condition, and define a contact set. Last week also I discussed this. You can have no penetration, bonded, allow penetration, likewise shrink fit, virtual wall. So last week I discussed the no penetration, allow penetration, and bonded cases. So here, if you want, you can do that kind of a override by selecting this face and this face, or else you can keep this as it is because I don't software has automatically selected the correct bonding mechanism. So if you want, you can suppress this and right click and define a contact set between these two faces. So I can ask the software to automatically find the contact sets, or manually we can do that. So it's no penetration condition. You can select this face and under this one you can select this face. So the same thing I'm doing in different ways. So so if you press OK now, it's the same thing. So this global contact here bonded and contact set no penetration is giving the same results. So if you want, you can suppress this one and unsuppress this. So both will give the same condition, same results. You don't need to suppress, unsuppress both. Have only one. So I hope you understood this. Global contact bonded means it's acting as a perfect bond here. Here I said no penetration, so this will not penetrate to the other. So whatever the contact method you can apply in this example. Then we will apply these conditions. So the bottom side is fixed. Bottom side is fixed. So we have discussed this earlier. Then top side is we give 1000 newtons vertically down. So 1000 newtons should be given. So we will give that as a force. So this way easily we can give 1000 newtons. So if you look at the book, they have given this 1000 newtons in a different way. If you look at the slides, 1000 newton load in the negative y direction. So y direction is this one, negative y direction, restraints in x and z directions. So if you give this kind of a loading, we don't restrain the motions in other directions, x and z. So you can give this kind of a load. Then what is the meaning of this load? It's vertically down in y direction, but in x and z direction we didn't specify any motion. So if you want, you can apply a fixture in x and z direction, or else in the slides what they have done is they have used this kind of a mechanism. We can give a load in y direction, but we can ask the software that there will be no movements in other two directions. There will be no other forces whatsoever in the other direction. So if you give this kind of a thing, we are giving only y direction 1000 newtons. XZ we didn't specify. But if you want, you can specify XZ also, saying that there will be no forces in x and z direction. So that's how they have given it here. So I will show you how you can give it in SolidWorks. So if you want, you can suppress this one also. Then we can give an external load using the same force conditions. There will be a tool called forces. This one. So I went to right click, prescribe displacements. Then I have to select on flat faces. Last week also we discussed this on flat faces, and we have to ask the software there will be no movements in these other areas. So we can give this kind of a condition. So in along face direction 1. So let me take this here. So I'm going to specify something like this. I'm going to specify there will be no motion in other directions. So we have to select this on flat face condition. So under forces you can select it, or under, so this is not like a force, you can go to fixtures and select this advanced fixtures. So advanced fixtures will also give you this on flat face. Or else if you go here and right click external forces and use the prescribed displacement, same thing will be coming on flat faces. So on flat faces, so I select this flat face and I say that there will be no motion in the normal direction. We can have motion, so I have to leave it alone. This is the normal direction. These are the other directions in other uh, x and in this case x and z. So I can ask this kind of a condition. So what I hope you understood what I am doing here. X enable here. Now what is the meaning of this one is, I gave this flat face here and I asked software that there can be more movements in normal to face. That is, there can be movements in y direction. Now this is the face. Normal means 90 degrees. So y direction there can be movements. But x and z directions there should not be any movements after we apply the load. So that's what they have given here. So if you say 0 millimeters, 0 millimeters here, the meaning here is in x and z direction there will be no motion, no displacements. If you give something like 1 millimeter here, the meaning here is in x direction there can be 1 millimeter maximum displacement. So after applying the loads, but here if you say 0, there will be no more, there will be no displacement in x and z directions. But here I am not giving anything in y direction, so that I am allowing y direction to change, y direction displacements to change. So this is how we give. Last time also, I think first week or second week, we discussed this on flat condition. Same thing can be given for cylindrical surfaces. So if you want, you can allow motions in radial direction, or you can ask the after applying the load, you can ask this to be rotated, or you can have it axially moved. Likewise, this case also discussed last week. So remember these kind of restraint conditions. So I'm not allowing motion in x and z directions. I'm allowing motion in y direction only. See, if you enable this, you are restricting all. Now I have restricted y motion also, then there will be problems because I am applying 1000 newtons, and I also say that there will be no motion, no displacement. So this will violate our conditions. So I have to leave it uh, disabled. So I hope you understood this, how we can give on flat face conditions. Any questions, let me know. So press OK. So what I have given here is, now I have applied a load, I have fixed the bottom, I have given some motion restraints here. In y direction only there will be freedom, x and z direction we restricted, and we can give external load. It should be now unsuppressed external load this side. So these are the things we gave. So you can apply these settings, and I will give you some time. Just apply these settings and please save your files. Sometimes it may crash. Next, we will apply the mesh and see what happens. So if you try to apply a normal mesh, we can do it. But here the critical area is this area. So this is the critical area, we need to get accurate results. So if you want, you can ask the software to refine the mesh and in that area. So we have done that here. So we have to ask the software to reduce the element size in this common area. In this common area, we can ask the software to reduce the element size. So if you want, you can right click here and apply a mesh control. We have done that last week. So we can select this face as well as this face and give a smaller element size. So here in this example, we have given 1 millimeter as the element size. So and press OK. So this area will be having small elements. So I have selected these two faces and gave 1 millimeter as the element size. So you can follow my slides and see what I have given. Then we have given a mesh control. So you can have a lot of mesh controls if you like. So you can apply another mesh control in other areas. But here the critical area is this common area. So I don't need to give other meshes. So if you want, you can create a mesh. Now we can clearly see that this area is element size are bigger, but when it comes to this common surface, I have selected these two surfaces. These element sizes are small. So you don't need to worry about these areas because these areas are not very critical. So if you want, if you think that this circle area is critical, just give a control to this area. Give a mesh control to this area. So here I'm not worrying about those. I'm worrying specifically about this common area. So if you have given that split lines in this design, you can select only that area. Here I haven't given the splitted lines. So I have to select the entire face. Here actually if you do the design correctly, you can split the part here, face here and give that area only the mesh refinement. So actually these areas are useless. Only this area is critical. So any questions up to this point? So we gave a fixed condition in the bottom. One flat faces here, forces 1000 newtons vertically down. Then we apply a mesh control. Right click and went here, apply mesh controls. Select the two faces here and gave a value here 1 millimeter. This is the aspect ratio. We have discussed this one. What are the meanings of these things earlier. All the things are in my slides. So if you find any difficulties, just go through the slides. All the meanings are given in the slides. Now we can solve this one. We can run the calculations. So I am getting a problem. No result saved. So I am having a problem here. I think the problem with these flat face conditions. We will see. I fix the bottom side. Here I have. We will see. We will suppress this global contact and enable contact sets. Sometimes this may be the issue. So I will remesh this. We will run and see. So earlier didn't get the results mainly due to this global contact condition. Its software said that the model is unstable. So what I did was I suppressed this global contacts and I applied this contact sets. So if you find any difficulties of applying this contact set, let me know. So I will. What I have done here is I have right click on this and went to contact sets. When you go to contact sets, you have to select no penetration and select this face, and under this box you can select the other face. So here we said no penetration between these two plates. If you want, you can have a bonded condition or love penetration like this. So that I there was a problem with this global one, so I applied the context. So this material is in this model the material is nylon. So any questions? Let me know about these conditions I gave. So I gave a contact set, then I gave fixtures, bottom side and top side. I have restricted the motion. Then I applied a load here, 1000 newtons down, vertically down. Then I mesh it with the control in this area. Then I run the results and got these von Mises results. So those are the things I did. Now I right click on this and edit the definitions. So we have to get maximum value, minimum value. If you want, you can plot the minimum value also. Then we have these floating numbers here. Then you will see the floating numbers. So maximum value is coming here. So you can see the maximum is here. The least, this area is very little, so that's why you are getting maximum stresses here. Now in the book, they have plot the contact stresses. So if you want, you can plot this area only. So here I'm getting entire diagram. This area is also somewhat critical. I said that because it's a circular shape, that stresses will be also going in this area. So this area is the problem. So if you want, you can change the definitions to contact pressure. So if you want, you can change the definitions to contact pressure, or you can plot a different plot. So I will keep this as it is. So now if you compare with the von Mises and yield strength, von Mises is less than yield strength. So I can have a small guess that this will not fail. But we cannot judge it from the first simulation. We have to run several simulations and see whether this is converge. This is a converge value. Even though this is less than yield strength, we cannot guarantee from the first results. So please remember that we have done mesh refinements last week. Do some mesh refinements and see whether this is exceeding this. So if you want, you can have a refined mesh and see whether this 129 is going beyond 139. So if I want, I can plot a new graph. So we can right click on this and right click here. So this results options, we can define, we can right click on the results and we can get a different plot here, stress plot, strain design, results equations. Mm, we will define another plot. Uh, I think the easiest way is to go to option C and define a plot. So we have discussed this one also last in the first day. Go to options and we have here three plots coming automatically. Those are the three plots here. So we can right click here and add a new plot. This plot is what Contact pressure is not shown, so we will not do that. It's not coming. So the easiest way to get the stresses contact pressure is we will right click here and go to edit definitions and change this to contact pressure. So change this to contact pressure, then press OK. You can see this area is the critical area. So the contact pressure is shown as 78.326 megapascal. So if you look at my slides, the arrows are somewhat bigger. So these arrows are somewhat bigger. In my drawing, it's small. So if you want, you can change these sizes. Go to edit definition. From this one, you can change the sizes. So if I press 400, you can see this is increased. So how did I do that? You will not find everything in edited definition. So you have to go to your vector plot option. So this is a vector plot. So you can see the arrows are shown. Vector plot. Go to vector plot here and change the vector arrow size. So if you let's give 300, this is the arrow size. 500, the arrows, and this is disabled at the moment. Otherwise, you can change the number of arrows here also. This is the result. So this area shows us the maximum pressure, contact pressure. So I change the definition to contact pressure. So you can right click here, go to edit definitions, and come here and change it to contact pressure. Earlier it was 1 meter stress. So if you just put to 1 meters, we will get the previous plot. Now the previous plot is shown as a vector plot. So you can see the arrows are formed. This is good when you analyze fluid mechanics, when you analyze thermal models. These arrow vector plots are better because we need to see the directions of the motion of fluid and the heat. But in the von Mises stresses, we don't need vector plots. So you have to change the definitions again. Vector plots we don't need actually. So we have to change this chart options to change it to say we need contact pressure again. Let's put the contact pressure, then you will see this kind of a result. Any questions up to this point? So when I change this to von Mises, I'm getting these kind of arrows. So that is not good in von Mises stresses. So you have to change this here again and come here and go to advanced and remove this tensor plot. Now you get this. So how you got that? Again, I will show you. You have to remove this tensor plot condition. If you put tensor plot under von Mises, you will get this kind of arrow. You will get a diagram with arrows. Tensor means something like vector. So you have to remove that tensor under advanced, remove this condition. And if you just go and select element values, what happens here is they will show you element wise distribution. So element wise, these are all the elements, so it will show element wise distribution. Otherwise, we can get it better, we get it node values. Then your plot is somewhat nicely uniformly distributed. The colors will be uniformly distributed. This is the node value results. So you can play with this thing and see what happens when you animate this. This is the scale is 1. You can see there will be stresses forming, and maximum displacements will be very little. Say I will go here and edit the definitions again. On the chart options, we have the plotting numbers 0.683689. So this area will give you the maximum deformation. So we can go to the definitions again and ask the software to show us the maximum and the minimum. Minimum will be obviously here. Maximum is in this area. This area is maximum. Anyone can answer my question. Why this area has the maximum deformation, not this area and this area? So those are the questions we need to know answer. So if you get the maximum displacement, we are getting the maximum displacement here, not here or here, but we applied same loads everywhere, 1000 newtons. So those are the questions we need to answer. So why we are getting maximum displacement here, this area, without getting here or here? So you have to think about those things. So that is the difficult part in simulation. So how can I avoid the maximum deformation here? Those are the questions I need to answer. So if you animate this, you can see how it animates. So we can slow it down a little bit. So this area tends to deform much more than these two areas. Are you okay with this example? Now I said that we cannot guarantee this one 129. This depends on the mesh sizes. So if I want, I can create a duplicate and refine the mesh and see whether the results are changing. So I will do that and see. I will take a copy and I will do a further refinement here. So we will change this mesh control and apply a small element size. Say I will apply zero point 0.5 this time. So we will create the mesh in that area. 0.5 size now, and I will run it and see. Now when I refine this, the stresses increase a little bit, 131. Earlier it was 129. So our design is still below the yield strength, so it will not fail. So if I further refine it, it may not exceed. So if I want, you can, if you want, you can have another finer mesh and see. So I will just edit this and say 0.25 this time. Create mesh. Now there is a problem. So sometimes the software will crash. So you have to save your work and do these things. If your computer is somewhat slow, like my one, there will be problems. So always have a good computer when you do this kind of simulations. So any questions about this exam, this contact stressors? We started with introduction to simulation and we did the static analysis of plate simple one. Then last week we discussed the L bracket and the link and the hanger. So hanger and contact stressors both used in the assembly file. Now we will look at the buckling one. So if you don't have questions in these areas, your assignment will be based on the static analysis. So I still didn't give the assignment to you because I'm still wondering uh, what is the level of assignment I'm going to give. So please be ready with static analysis for the assignment. Then we will look at buckling analysis. I have to on the task manager. So we will start the new topic, buckling analysis. So here we have we are going to do buckling analysis as well as static analysis for the example for the model. So we have this kind of a condition. So this is a I-beam bend one. So we have fixed this. We have fixed this surface here, and I'm going to apply 2,500 newtons to this one. So when I apply this load, what will happen to my I-beam? So I-beam will be deformed. So it will be deformed in this way, in vertical, in along the same plane, it will deform. So and we can get the safety factor of safety. And from the structural simulations, we can say this is structure is safe from the static simulation. But especially in these kind of beams, there can be buckling happen. So there will be buckles. So you have to analyze that one also in simulations. So you have to do a buckling analysis and see whether this is going to fail in buckling analysis also. So we have to check whether this is going to fail first from buckling or uh, stresses. So we have to decide whether this is going to deform in static or in buckling. So here we will do both cases and see what is the first occurrence. Whether the first occurrence is a static deformation or buckling first failure. Actually, the first failure happening from the static deformation, no first failure happening from the buckling deformation. So that's the example we are going to do. So when you have beams like this, especially remember that we have to analyze this in buckling also, not only in static analysis. So if you have a structural elements like I-beam, L-angles, box bars, try to do buckling analysis also. Don't only depend on the static analysis. So first we will do static analysis and see. So I have given you a file called I-beam. This is the I-beam. I hope everyone can draw these kind of things now. This is drawn from sweep tool. Easily we can draw the I shape and do it, or else here they have used structural members weldments. So directly they have used the welding methods in SolidWorks. So we haven't done that in our class. So you have area called weldments here. So they have directly used that libraries. So we haven't done this area. So if you don't know how to use the libraries, just draw the I shape and apply a sweep. Then you can get this shape. So I will start the static analysis. Now, normally in beams like this, software treat this as a beam element. So you can see two dots are forming. That is when you have designed something from a welding weldments, like you have designed this from weldments, structural members. So this is a structural member coming from the SolidWorks library. So if you use this kind of a structural member from the libraries, software automatically thinks this is a beam element. So when in the first day classes, I have told you that we have an element called beam elements. So in the first day classes, we have mentioned about three kinds of elements: solid elements, shell elements, and beam elements. So if you have done this using structural analysis, software will automatically think this as a beam element. So in this example, we are not going to do that. We are going to treat this as a solid element still. So what we can do is we can now this is the problem. They are taking this as a beam element. So we can right click here and treat this as a solid element. So you can get the same results, but here we haven't talked about the beam theory still. So we will treat this as a solid. So in our slides also I have mentioned that. So convert I-beam to a solid element. So here convert I-beam to a solid. So we can use the I-beam theory and do this, but here we haven't done the weldments and other things. So that's why we treat this as a solid element. So we can right click here. You will get the same results at the end. Treat this as a solid element. So once you do that, automatically the elements will be in tetrahedral elements. So we will now fix the side here. Fix this side. So if you think that these arrows are converged, you can come here and change the arrow sizes also. So I can reduce the density. So this kind of a arrow density can be reduced. 20. So there will be less arrows here. If you think that these colors should change, just come and change it. So lot of possibilities are given. Where is 100? So you can see how it changes to 100. Okay. So I fix this side. Then this side I should apply. I hope everyone understood why I did this treat as solid, because I want to analyze this as a solid element, not as a beam element. So I will open this again and show you what I did. This was the file. Now I went to new studies, static. Automatically software thinks this as a beam element. So you can see when you expand this one, this beam element symbol appears. This is the beam element symbol. So I can right click and change this to solid. So when you change this to solid, this symbol changes. You can see this change to solid. So it's mentioned in my slides, this symbol will change from beam to solid. So that's what I did. Then I came here and fixed this side. Then this side we should give 1000 newtons the end fix. So we will give that. So when you look at mesh here, they have given here standard mesh size 8 millimeters. So depending on the solid sizes, we can decide this 8 millimeter standard mesh given. So and press OK. Element size is 8 millimeters. So just give that value. Then the von Mises results can be plotted. Save your files. And I will put these numbers in floating values. Now this is the one Mises result. So if you look at the one Mises results, it's way down yield strength. So you may think that this is not going to fail under one Mises results. So I gave 1000 newtons, and when I animate this, I will see something like this. So this animation happens along the same line, so it will not buckle. So it just deform in the same direction. So the maximum values will return here. Maximum value will occur here, 47.6. So sorry, I have to apply not 1000 newtons, 2500 newtons. So I made a mistake. This value should be applied 2500 newtons. So I will edit this value. This is 2500, and you can rerun this. So you can get a results higher than the previous value, 190. So we can think that this will not fail under this loading condition. So when you look at this factor of safety, it's 1.75. So my value is 119. So in the book, the slides, we have 118. So the structure is safe under this loading condition. So you can think that under static analysis, the structure is safe. Are you okay up to this point? Now, in the slides, I have shown you the previous original shape also. This is the deformed shape, original shape. But when you look at my simulation, I can't see the original shape. So if you want to see both original shape and the deformed shape, there is a way in SolidWorks to do that. We have to go to edit definitions. There is a tool here under settings, which is called superimpose model on deformed shape. So we can apply this one and have the transparency around 20%. So when you apply this transparency, what is the meaning of this transparency? That it means you can have a slightly shown original shape in this area. So when you apply the transparency, the original shape will be also shown. So I will animate this. You can see how the original shape is now shown. So when you animate this, you can see that. So I will go to edit definitions, go to settings here. Say superimpose value may be around this much, 30%. Now you can see the original shape here. So you don't have it something like this, then you will see a very clear original shape. So have it around 40%. It's a judgmental value. So you can see the both original and the normal shape, deformed shape. So when you animate it, you can clearly see how it's changing. But mind you, this is 15% scaled up. So if you want, you can have original sizes even. I can come here and have this true scale. Or one to one scale. When you apply true scale, you may not see the deformation clearly. I will animate. Can't see clearly. So that's why we need to have a higher scale. Otherwise, sometimes it's very difficult to see. So when you can come here and go to superimposed model and have something like 0.4 and see both the shapes, original shape and the deformed shape. So and when you animate this, clearly I can see the changes. So the changes happening along this direction. It will not buckle. So I can say that the structure is safe under static conditions, but we cannot guarantee, since this is I-beam, we cannot guarantee whether the structure is going to save. So we have to run the buckling analysis also. So we will see how to run the buckling analysis now. Any questions up to this point? So we treated this as a solid. Here we can convert back it to beam also. Then we fix this side and we get 2500 newtons here, and we mesh it using 8 millimeter size, element size, then got something like this kind of a result. Any questions up to this point? So I showed you how to change this to superimpose mode, superimpose, and this value can be adjusted. When you adjust this, you can see original one and the deformed shape. Don't have it something like this, then you can't see it. So the transparency will be reduced. Then we can animate this and see how it deforms. So we will now apply buckling if you don't have questions. So I will run a new study now and do a buckling analysis. So this is a new area we are going to discuss, buckling. So I hope you have done some theory based on the buckling when you do your theory classes. So here also we have to treat this as a solid. And if you want, you can copy these fixtures and measures. So what we can do is we can drag and drop the fixtures here. I'm going to copy. This is taught in the previous classes. And forces also I can drag and drop to this buckling analysis. Then if you want, you can drag and drop the mesh even. So I treat this as a solid, then fix this one and apply a mesh, and apply the load. So what we did was, I didn't do it again and again, we just drag and drop it through. So I hope you can remember the things I did in the previous class. Drag and drop. We cannot duplicate because these are two different studies. So buckling is given, and if you look at the properties here, we need to normally when we run the buckling under properties, we need to give buckling modes. Like when we apply frequency analysis, we have to give the modes. So normally we have to give at least 5 modes in buckling analysis. So when you do some buckling theory in theory classes, they are getting results for at least 5 or 3 buckling modes. So we have to do that in the software also. Just remember this one. When you do a buckling analysis, normally you have to run 5 modes. So you can easily right click on this and go to properties and apply 5 buckling modes. So it's similar to frequency analysis. Now I copied the fixtures, copied the hoses, copied the mesh, treated this as a solid one. Then I went here and changed this to 5 buckling modes. Okay, now we can run this. That's all we have to do. Now actually these will show you the 5 modes. So here we don't worry about that one greatly. These are the different modes. Now when you apply that load, what happened to my design is under different buckling, different modes. So you can see how it deforms. So my beam wheel twisted in these directions. So you can see when I animate this, after the load applied, the beam wheel twists this way. So it will buckle. So in the third amplitude, when you animate, what happens to my design? It will twist it. It will twist like this. It's taking this. So under static analysis, we didn't see those kind of situations. Static analysis only it's deformed in one direction, but in buckling analysis, we see different deformations under different modes. So my design is subjected to different deformations under different modes. Now that this is like a frequency analysis. So you have different modes. 5 modes we have analyzed. So in each and every mode we have different deformations. So when you right click and uh, look at the buckling safety factor, now you have to look at this one. Not the deform shape is the critical thing. You have to look at the buckling safety factors. So when you look at the buckling safety factor, you have to look at the first positive buckling safety factor in the SolidWorks simulations. So this is really critical. So the negative values, we have to look at the first smallest positive value. So negative means the load is in the other direction. So that's not a big deal. So that's why we are getting negative values. The vector, there's a vector. So vector direction is different. So you can see the minimum safety factor is 1.31. So if you look at my static analysis, that safety factor was 1.75. So the static analysis safety factor is higher than the Buckling analysis safety factor. Buckling analysis safety factor is 1.32. So here the conclusion is buckling is the deciding mode of failure. If you have to look at buckling safety factor versus the static safety factor. So if the buckling safety factor is less than static safety factor, your structure will fail under buckling before the static fail. Okay. So if the buckling safety factor is higher than the static safety factor, it will fail under static loading. So in this example, it will fail under buckling loading. So remember that it will fail under buckling loads. Any questions about this? Now I have to run two simulations. I did the static analysis and got static safety factors. Static safety factor is 1.75. This is the static safety factor. Then I did a buckling analysis. We had 5 modes. We can right click and change the modes to 5. Normally we run 5 modes. Then we got 5 different plots. These plots will show you the beam is now twisted in different directions under different modes. But if you want to critically analyze this, you have to right click here, get the buckling safety factor. So this negative value shows that the beam for direction is different, the force direction is different on the first and second modes. But you will find the lowest buckling factor is 1.31. So it's less than this static value. So my design is failing under buckling modes. That's my conclusion. So you have to do two different analysis for this kind of beam structures and see whether it's going to fail under buckling mode or under static mode. So clearly it shows the static deformation happens in a single plane, but in buckling deformation it's happened in a different plane, so it will twist. So any questions about this? So the conclusion is when you have buckling, when you have beams to analyze, do a static analysis as well as a buckling analysis and compare the two safety factors. So if the buckling safety factor is less than the static safety factor, your design will fail under buckling. So any questions? If you want to follow, repeat this or tell me. So these tables can be saved under Excel file. So you can save it as Excel file and open it in Excel. Those facilities are given. Any questions about the examples I did? So you have to remember when you analyze a beam, just do buckling and static analysis both and decide what is the dominant failure mode, whether it's a static failure or buckling failure. And then if it is failing under buckling, you further analyze your simulation in buckling. If it is failing statically first, just analyze it further in static modes. So we will look at another topic if you don't have questions in this area. So our last topic for today is the static analysis of a bracket using adaptive solution methods. So this is the last topic under static analysis I am going to discuss. since we are doing some 2 hour or 2.5 hour sessions, I may have additional time left in the future classes. So if you have any questions, we will discuss about those things later. If you have any questions about modeling, I heard that some of you have questions in modeling. So we will discuss them in a different session since I have some additional time left. So we have to discuss fluid theories also. I will try to have some face-to-face classes after this. Probably next month it will be over. This corona problem will be somewhat over. So we will be able to have some face-to-face sessions also. So we will try to meet and discuss the questions we had in the previous, especially in the modeling class. So for the time being, since I'm not using 4 hours. Last week also I didn't use 4 hours. This week also I'm not using 4 hours. So we may have some additional time, so we can discuss those issues after we meet. So we will look at this adaptive method. Then what is the meaning of this topic is we can ask the software to do some automatic mesh refinements. Earlier when I did it, I manually changed the mesh. I manually control the mesh. I change the element size manually. But there are ways of doing it automatically from the software itself. So there are two methods available. One is called H adaptive method, other one is called P adaptive method. So under H adaptive method, simply speaking, what he does is he is trying to analyze the critical areas automatically, and software automatically tries to reduce the element size in those critical areas. So if you look at this example, this area is the critical area, the fillet areas. So I am applying a load here. So the software automatically refine these areas. We will not worried about these other non-important areas. So that is the H method. If you talk about the P method, P adaptive method, he will try to increase the order in the elements. So if you just participate to the first class, I have mentioned what is the meaning of order. Order is uh, first order element, second order elements. So we have something like first order and second order in solid. So in P method, he is trying to increase the order of the elements and try to get an accurate result. Automatically this is happening. So we can ask the software to do this automatically. Then it will reduce our time also. So we will first look at the H method, H adaptive method, how it works. So we will open this model and see first. So on the chapter 8, I have given a file called bracket. So we have given some fillets here, and you can see a lot of split lines have been given. Split lines which make sure you are giving the loads only to the same. So if you suppress this split tool, you can see I cannot give a load to this area. So that is the usefulness of splitting tools. So we have discussed this how to create splitting lines in SolidWorks when we discuss the theory classes. So I will do a static analysis now. So what are the loading conditions we have? We have to fix this side and apply 10,000 load Newton uniformly distributed. So before we we will create a static condition and start this. So we are going to look at some different cases. So first case is we will rename this as H with H elements, H adaptive elements. So static curve analysis with H elements. Okay. We can fix the backside and apply a load 10,000. Then if you look at the properties here, now we have to change this to this H adaptive methods. Earlier it was none. So we will look at what are the cases we have to do. Okay. So we will not run the H element first. We will just run a normal one. Say without H elements, we will run the first case. So I will just run the first case without H elements. In the slides we have mentioned it really. So we will run these cases using one mesh of H elements. So what we are going to do here is we are just run the second order tetrahedral solid H element with default element size. So we will do it with the normal default element size first. So what we are going to do is we right click on the mesh, create mesh, and go to default meshes and press OK. Now this is, you can see everywhere the element size is same, and we will run this and get the results. We will have it plotting numbers maximum. Now this is the value 67.181. So the maximum value occurs somewhere. Even though we have introduced the fillets, maximum value comes out somewhere. So we have to refine the mesh in these areas because those are the critical areas. So we can ask the software to automatically do that. Now I did just a normal mesh. So we right click and we went to create mesh. We just use the standard meshes. We didn't even select the curvature. Just press OK and it is normal mesh. So I hope everyone can do this now. Now we have to do second one is this is the say we can rename this as scan. Now we will duplicate this one and create a H adaptive mesh. Second one is H adaptive mesh. Sorry, not H adaptive. We will do standard plus some mesh control. So I'm going to manually control. So this is the normal one, standard one, and this is the mesh. I'm going to have a mesh control manually in these areas. So we can copy these constraints. What I'm going to do is I'm just copying this fixture here, and I'm going to. Sorry, no need to copy. We did duplicate it, so we don't need to copy. All the things are coming. So I duplicated, that's why I got all the things fixtures and loads coming. Then we can have a mesh control. Apply some mesh control in these areas. So those areas are the critical areas. So the element size is 3.9. So that area you can see the mesh is now small. So you can run it. If I'm going fast, tell me. So now the result is 76.52. So earlier the default sizes given, the results was 67.8. So you can see the when I refine the mesh, my stresses are increased. Still it's a way below the yield value. So I went to the second one. I applied the control here, mesh control. What I did was I selected these two faces and gave a default mesh size 3.9. This is automatically coming. Earlier it was 7 point something. So if you look at the previous mesh size uh, definition, it's 7.8. So when you control it, automatically it divides to half, 3.9. So earlier mesh size is 7.8. 7.8. You run the simulation, you got 67.81. Then the next one is I'm copying loads and fixtures. I duplicated it, then I applied the mesh control. That control value automatically takes 7.8 divided by 2, 3.9. Automatically it comes. Now I got some results like this, 76.6.52. So you can clearly see stresses are increasing. So these two did by myself. So I did the standard mesh and I control manual. Any questions up to this point? Still I didn't start any H adaptive or P adaptive methods. So I did the previous class theories. So we did this one, standard size. Then we applied some controls in these areas manually and got this result. Any questions? Now we will look at the H method. So if you want, you can copy the things, but better we create a new study. So this is now this is with H adaptive. New one. So we can simply copy the features, just drag and drop, and we can Copy the forces, drag and drop. I will not copy the mesh. So because I will ask the software to automatically do this. Edge adaptive. So we are going to right click on this and go to properties. So right click on static, go to properties, and we will see the adaptive methods we are going to discuss. So earlier in the previous two cases, we used the none method. None method means manually I did the refinements. Uh, Now we are going to look at how to use the edge adaptive method. So when you enable the edge adaptive method, these criteria are coming. So target accuracy. So what do you mean by target accuracy is if you put this to the high side, that is your answers are accurate more than this side. So if you put this into lower side, your accuracies are low. So if your default value is 98%, uh, you can get more accurate stress results. So here this says accuracy bias, it's in the middle. So if you put this into global one, your answers are more accurate. If you put into local areas, what I'm talking here is given in my slides. What do you mean by target accuracy? What do you mean by accuracy bias? Maximum number of loops, mesh coordinate. So all this information is given in the slides. I'm just explaining very simply. So if you put this into local areas, your accuracies are actually low. If you put it in the middle, uh, it's the medium accuracy you are getting. So you can have it under this area, global area, but your processing time will be increasing. So this will get more accurate results. Then the number of loops, that is how many loops this calculation will run. That is software will try to get more accurate results when it have more loops. So maximum number of loops are 5. So he will try to converge the result 5 times, or he will try to get more accurate results 5 times. So better you have that 5 here. Then mesh coarsening. If you tick this button, what is the meaning of this button? If you tick this button, now this area is not really critical. So he will not concentrate on these areas. Uh, this is the critical area, fillet area, or else this area. So if you apply mesh coarsening, he will not apply fine meshes here. He will just apply normal meshes. If you untick this one, he will not consider that even. So it's up to you to select this one. No. So if you apply this one, uh, we will change the mesh sizes here. So we will keep these settings and run it and see. So if you want, you leave this one because this is a simple example. Just leave it. Have this one 98% and global side and number of loops 5. So press OK. Now its adaptive method is given. So you can just run it and see. Or else you just come here and create the mesh. Now, if you do this way, what happens is we are just coming back to the normal situation. So you don't see any refinements. So we cannot do that one. You just right click and run this. Then you can see software will using edge adaptive method. Is running 5 times. So you can see this is increasing 75. Again he will run. Now this time it takes much more time than the previous 79. So you can see it's increasing. It's refining the mesh. Still running. $79. Analysis has satisfied the current HLFT accuracy 90.8. You may increase the target accuracy to read. So we got something like 78. So adaptive method stresses we can so this is the plot I can get. So I hope you understood. I'll show you how to get this plot again. So this is the number of loops. In the first, when it comes to the second loop, you get the maximum value, 79. Then in the other loop, it's going down. That is, now when it comes here, it's going down. So this is the maximum value we are getting. So no point of running other loops. That's why it stops after 3 loops. I gave it. I need 90%, 98% accuracy. So I got something like this kind of a result, 79 in the in the second loop. So no point of running again. So after third loop, it finishes. So if you try come and change these accuracy levels to say 99 or something, 99, you cannot have 100% accurate results. 99, say I will put it in here also more for the far away right side. Then run it again. We will see whether this is going to change or not. So you may think that this is really easy. You can ask the software to do this automatically. Actually, this is somewhat easy. So if you have the knowledge of the previous refinement methods, you can ask the software to do this automatically. So then you can expect more accurate results. But you need to know the fundamentals. That's why I taught you the fundamentals in the first few days and started this topic. So this is an automatic tool which will reduce your time. So you can right click on this one and get refine adaptive convergence plot. So when you click here, we can get the plots in whatever the way we like. Say I want to get a plot of maximum 1 meter stresses. That's okay. You can see now this time he has run 4 loops and the maximum value is coming here 79. So you don't need to run the others. So it's going to be constant. So under this refinement, we will get the maximum. So I hope you understood this. So early cases, we had maximum value 76. First one standard value is 60 something, 67. So which are not accurate. So the most accurate one is done by the software, which is 79, around 79, 78.48. So this is the most accurate value under this loading condition. So we had 2 graphs, same graph actually. So we right click and get this convergence line. Any questions about this? So remember these settings. If you cannot remember anything, just go through my notes. What are the meanings of this? So this right hand side is more accurate results we can get. So if you look at our mesh now, we can visualize the mesh. Show mesh. You can see how he has done the refine. Automatically the software has refined this area heavily. This area he has refined heavily, and even this area he has refined. So we may not think about these areas. Oh my. So you can see how nicely he has done it. Inside also he has refined, but not in the middle area, these corner areas. So this is the beauty of automatic tool. He will do it nicely for you. So we will, if you don't have question, we will run the solid P methods also and see. In the P method, he is trying to change the order. So I said that we have second order and first order element, but in P method, software can go up to fifth order. So it's not available on normal meshes. So we will create a P study. This is P adaptive method. P adaptive, say standard P adaptive. See P adaptive. Okay. Now I will copy the loads from the first one. Fixtures I will copy, and the loads also I will copy. So I copied the fixtures and the loads uh, standard from the standard one. Now I have to change the settings to P methods. We will go and check the properties. Adaptive, P adaptive. So P adaptive, it says something like this: stops when total strain energy changes 1% or less. That is, when he runs this one iteratively, you have to compare the first steps results and the new step results. So if the results is less than 1% change, you can stop the iteration. Starting P order is 2. The order of the differential equations maximum is 5. Maximum number of loops are 2 to 4 is 2 to 5 is 4. So you can run this default settings and see what's going to happen. Press OK. Then we will run this. Don't mesh it, just run it. We will do iterative. We will iteratively run the process. it comes as 71. So we will have floating numbers. 71.63. So under default P settings, I've got 71.6. But if you look at our mesh now, so we will just apply the mesh. You can see the mesh is not refined as the previous case. Previously, H adaptive, uh, he refined the mesh. But in P adaptive, he is not going to do any refinements. He is trying to change the order. That is, he is trying to change the shape only. We will have some flexibility among the elements. So if you look at the uh, details of the mesh, uh, under P, we have element size is 7.1. You have total elements 7,729. Aspect ratio is very good, 100% less than 3. So we have total elements 7,720. If you look at the previous H adaptive method, elements number of elements will be how many? 120,000, 22,182. So very huge compared to the 7,000. So that's why your H adaptive methods are far more superior than the P adaptive method. H adaptive method is trying to have a lot of elements in critical areas and tries to get a lot of good accurate results. Element size is you can see it's 7.8, but the number of elements are the important thing. So when you compare the mesh results, mesh details, clearly you can see the difference. 7,000 against 120,000, and the aspect ratio is here 3.8, somewhat big. But if you look at this one, its adaptive aspect ratios, it's also 3.8 maximum. But the critical thing is here is the mesh number of elements. So if you look at it clearly, I can see a lot of elements have been applied to the critical area. But in static P adaptive method, if you look at the mesh, it's uniform. So if you want, you can now this 71 is not really uh, believable. So I can have a conversion graph and see. So we will get a conversion graph under one meter stresses. You can see it's not converging. So in the second loop also it's climbing. So you cannot trust this well. It's not converging. It has only run 2 loops, not even 5 loops, 4 loops. So we have to run several loops. So what we can do is we will uh, refine the settings. We will create a duplicate. I will have a refine mesh. Refine P adaptive. What I'm going to do is I will come here and change the properties to this accuracy. I'm going to reduce accuracy. I'm going to increase. So what we can do is we can in the book we have given this much of accuracy 0.01. So we will give 0.01. So the meaning of this one is when you compare the two iterations, when you compare two iterations, the first iteration and the second iteration strain energy change should be less than 0.0. So if it is less than 0.01 only, this will stop. Earlier it was stopped when it was 1. Now I can press OK and we will run this and see. Now this time there will be more than 2 loops. So we allow maximum of 4 loops. We will see whether it's going beyond 2. Earlier it stopped at 2 because it reached that strain level condition. Now it's going to third level, third loop. We should go to fourth loop because we gave a very little value there, 0.0. Fourth loop it went. Now we can see the results and see. Now it climbs to 72. Earlier it was 71.6. It climbed a little bit. And if you look at the mesh details, show mesh, it's a similar mesh. Mesh details, elements are also still hanging around same value. What he tries to do is he's trying to shape up the element. So there is no other way in P. So he is not increasing the elements, he is just trying to shape up the elements. So we will see the conversion plot. Stresses. Okay. You can see it tries to converge. Earlier it was a rapid increase. Now it's trying to is achieving some stable value, but still not. We didn't come up to the value we got from HRW. HRW we got 78. Still he is not coming to that level. Still he is in 70. So what we can do is we can try to refine that value again, but no point of going behind P method. We can have 0.001 know this error we can reduce to 1%, something like that, and see. We will do it and see also. Duplicate. Another refinement we will apply. Apply to change the properties here and come like say 1%, sorry, 0.5% error. But personally, I believe that H-adaptive method is better than P-adaptive because H can increase the elements, number of elements. P cannot increase the number of elements. He is only trying to shape up the element, change in the order. So P will not achieve that accurate results like H. So it depends on the cases you do. If you are doing a very critical design, you go with H-adaptive. Otherwise, if you are doing something like a basic design, go with P-adaptive because H-adaptive will take a lot of time when it comes to the number of elements. So these models will not show you a lot of time, say time waste, but when you do complex designs, it will take sometimes days to get the simulation results out. So not few minutes, sometimes few hours will be taken. So if you are doing a air condition modeling or fluid simulation, sometimes it takes a lot of time. So it's again 72.3. So it's not going up to 70.2.8. So my conclusion is now I can get a plot and see. It will converge, but we were having a restriction here. Number of loops are 4, so we will not going get that much more accurate results like H-adaptive. So any questions about these two methods, H-adaptive and P-adaptive? So it says under comments, experience indicates that second order H elements offer the best combination of accuracy and computational simplicity. For this reason, SolidWorks simulation automation is turned to create H elements. P-adaptive solution is much more computationally intensive than a standard or adaptive H element solution. For this reason, the P-adaptive solution should be reserved for special cases where solution accuracy must be known according to the settings available in the P-adaptive style. So you actually try to do H. P-adaptive is not really, I can't say good. H-adaptive is better than P-adaptive. That's the end of our simulation here. Any questions about these 5 cases? We started with the normal setting, then we had the control around the fillets, then we adapted the edge adaptive method, uh, 99% accuracy, then we uh, changed the edge adaptive settings. So we went to P adaptive, then we refined the P methods also. Any questions? So in your syllabus, we have almost completed the static part. So we have to do that fluid area. So I will let you know whether I'm going to have the fluid sessions next week or whether we are trying to have a face-to-face session and do the fluid sessions. So we have to do some fluid simulations also in SolidWorks. So apply CFD to simulate design aerodynamic problems, define the problem. So we have 2 more days left. So I will try to start fluid next week or uh, we will look at the situation and try to have some face-to-face sessions also. So I have covered some areas in static in the last 3 days. So if you have any questions on the modeling, also let me know. I will try to help you. So always look at our videos. We have uploaded everything to the YouTube. So I hope you know our channel and the links were shared. So last week YouTube lecture is also available. Just go through the things. Everything is recorded. So this is the last week lecture, previous one. So we have the playlist. You can go to the SolidWorks playlist and see other videos I have done. Not only your videos, our street graduate videos are also there. So if you find any difficulty of modeling, go through these detailed specific areas. So if you have a problem with coordinate system, just look at the coordinate system uh, clip. It's only 3 minutes. Point theory 6 minutes. Axis theory 4 minutes. Likewise, we have small sessions and fillet tool only 24 minutes. Fillet expert 6.8. So some tools I haven't done with you. Tutorial only 9 minutes. So if you have a problem with this tutorial, just look at this video. So everything is nicely given. It's up to you to go through these things and get an understanding. So these tutorial wise videos are given. This is for our street graduates. But you can look at the same thing. Some assembly drawing methods also given. If you are interested in assemblies, just go through this thing and learn. So we will wind the class for today. So any questions before we stop? So if you don't have questions, I will stop for today. So I have some hours left, 2 days fully left and some hours left. So we will try to cover the difficult areas and the CFD theory in the coming lectures. So I will stop for today. Thank you for coming.